Welcome to partial derivatives. So partial derivatives in multivariable calculus can be defined similarly to derivatives in single variable calculus. So if we have a function f of xy, then the partial derivative of f with respect to x is, we often denote it as f with a subscript of x for a partial derivative of xy is equal to the limit as h goes to 0 of f of x plus h comma y minus f of x all over h. So essentially we're viewing, f of xy all over h. So essentially we're viewing y as a fixed point, and only looking at sort of the derivative in the x direction. So if we go a small increment in the x direction, we keep y fixed. This is our partial derivative with respect to y. Sorry, with respect to x. The partial derivative with respect to y is defined similarly. So the partial derivative with respect to y is, we often denote it f with a subscript of y of xy is equal to the limit as h goes to 0 of f of x comma y plus h minus f of x comma y all over h. So in this case, we're leaving x fixed. It's not at all involved in the limit. We're essentially having two y values very close together and finding the slope of the secant line between those 2 points. So we have one in the x direction, one in the y direction, and we hold the other variable fixed. In practice, to find the partial derivative with respect to x, simply treat y as a constant. So no implicit differentiation needed, no chain rule needed. We're just treating y as a constant. Similarly, to find the partial derivative with respect to y, we treat x as a constant. So to find the partial derivative with respect to y, just treat x as a constant. So for example, let's consider the function f of xy is equal to 3x squared y minus 5xy cubed plus 2x. Our job is to find the partial with respect to x and the partial with respect to y. So to find fx, the partial with respect to x, we treat y as a constant. And take the derivative with respect to x. So if we have f of xy is equal to 3x squared y minus 5xy cubed plus 2x, the partial with respect to x of xy, 3x squared will go to 6x, and then we have times y. So I'm actually going to write this as the derivative with respect to x of 3x squared, and then times y. Then we have minus the derivative with respect to x of 5x times y cubed, then plus the derivative with respect to x of 2x. So the y is literally just coming along for the ride as a constant. Right? So this becomes, we have 6x times y minus 5 times y cubed plus 2 as our partial with respect to x. I need to give myself a little more room for the partial with respect to y. So now let's do to find fy. So this is to find the partial with respect to y. This time around, we are going to treat x as a constant. And take the derivative with respect to y. So we have a partial with respect to y of f, evaluated at xy. Actually, before we do the partial, let's just rewrite f of xy was equal to 3x squared y minus 5x y cubed plus 2x. So if we want to find the partial with respect to y, 3x squared is acting as a constant. We take the derivative with respect to y of y. And we have minus 5x acting as a constant. We take the derivative with respect to y of y cubed. Finally, 2x itself is a constant. So this is essentially like 2x times 1. So we're going to take the derivative with respect to y of 1. So we have derivative of y with respect to y is just 1. So the first term is simply 3x squared. Derivative of y cubed with respect to y would be 3y squared. So we wind up with minus 15x y squared. 2x is just a constant. Take the derivative of that term, it goes to 0. Right? That 2x is a constant, it has no y's in it, as long as we are viewing x as a constant. So our partial with respect to y is simply 3x squared minus 15xy squared. So this is a useful trick to use, or this is much faster than having to do the definition, the limit definition of our partial derivatives. Again, you're just viewing the other variable as a constant and taking the derivative with respect to whichever variable we're working with. So now let's go ahead and move into 3 variables, exact same thing. I didn't actually write the state question. The question was supposed to be find the partial with respect to x, the partial with respect to y, and the partial with respect to z. So here we have the function f of x, y, z is equal to 2x, y, z squared minus 3 cosine of x, y plus natural log of the absolute value of y plus z. So to find the partial with respect to x, we're going to view y and z as constants. and then differentiate with respect to x. So we have our f of x, y, z was equal to 2x, y, z squared minus 3 cosine of xy plus the natural log of the absolute value of y plus z. If we're viewing y and z as constants, then that natural log of absolute value y plus z is acting like a constant. So we're going to view that last term as a constant. If we take the partial derivative with respect to x, we have fx evaluated at x, y, z is equal to the 2 y and z squared come along for the ride. The derivative of x is 1. So we just have 2 y z squared. If we wanted, we could do 2yz squared times the derivative of x. This next one is a little bit weirder because we do have a chain rule involved. We'd have minus 3, cosine goes to sine, so it will be plus 3 sine of xy. And then we multiply by the derivative of xy, viewing y as a constant. So this becomes times y times the derivative of x. And then, of course, the last term goes to 0. So this here, we're applying the chain rule. On minus 3 cosine xy. And we don't have to then multiply by the derivative. Again, unlike with implicit differentiation, we're viewing y as a constant, so we don't need to worry about product rule. So we wind up with the partial with respect to x, evaluated at x, y, z, should be 2yz squared. Then we would have plus 3y sine of xy. Sorry, sine of x times y. So this is our partial with respect to x. Then we move on to the partial with respect to y. So to find the partial with respect to y, we view x and z as constants. And differentiate with respect to y. So again, our f of x, y, z, we had f of x, y, z was equal to 2x, y, z squared minus 3 cosine of xy plus the natural log of the absolute value of y plus z. So this time around, every single term contains a y, and so we do have to differentiate each term. None of them are constant. If we take the partial with respect to y of x, y, z, this first term, we just have a 2x z squared acting as a constant. then we'd multiply by the derivative with respect to y of y. For the second term, again, we apply the chain rule. -3 cosine goes to a +3 sine of xy. And we have to multiply by the derivative of that xy. X is acting like a constant. We multiply by the derivative with respect to y of y. Finally, again, we have another chain rule, the derivative of the natural log of y plus z. Natural log goes to 1 over y plus z. Then we would multiply by the derivative with respect to y of the y plus z, essentially, viewing z again as a constant. So it would be times the derivative with respect to y of y plus the z just goes to 0 if we're viewing it as a constant. So this becomes, we have 2x z squared plus 3x sine of xy plus a 1 over y plus z. So this was our partial with respect to y. Last up, we do our partial with respect to z. So for our partial with respect to z, we view x and y as constants. And differentiate with respect to z. So differentiate with respect to z. So we have, again, f of x, y, z is equal to 2xy z squared minus 3 cosine of xy plus the natural log of the absolute value of y plus z. So again, x and y are acting like constants. So that means this minus 3 cosine xy, which has no z's at all, is going to behave like a constant. We view as a constant, that -3 cosine xy as a constant. When we go to take our partial with respect to z, the 2xy is acting as a scalar multiple, and we multiply by the derivative with respect to z of z squared. That middle term just goes to 0. Then the natural log absolute value of y plus z will go to 1 over, and then we have our chain rule. So we have 1 over y plus z. Then we multiply by y is acting like a constant, so that'll just go to 0. And then we have the derivative with respect to z of z. So we should get that our partial with respect to z is 2xy times 2z plus 1 over y plus z, otherwise known as 4xyz plus 1 over y plus z. So this again is just finding that partial derivative with respect to x, y, or z. It's a very basic derivative. It's literally just taking a derivative, viewing all other variables as constants. So it's simpler than implicit differentiation. We don't have to worry about any of our chain rules falling out, anything involving a different other variables than the one we're focusing on act exactly like constants when we take partial derivatives. In the next video, we will go ahead and look at taking higher order partial derivatives, and sort of what happens or how we can mix and match. We can take a derivative with respect to x and then a derivative with respect to y, etc. when it comes to partial derivatives.